Hi Year 13, Mr. Vinault here again. In this video we're going to look at the periodic table and we're going to look in depth at some of the trends on the periodic table. All of those trends depend on the same factor. They depend on the electrostatic attraction between the protons in the nucleus and the valence shell electrons. So all of the trends that we're going to look at, they all depend essentially on how attracted the nucleus is to the valence shell electrons. So there are many factors that can affect how attracted the valence shell electrons are to the nucleus. The first factor is the number of protons in the nucleus. If there are 2 protons in the nucleus versus 7 protons in the nucleus, the atom with 7 protons has a greater nuclear charge or more positive charge in its nucleus. That is going to have a greater attraction to the valence shell electrons. The second factor is the distance of the valence shell from the nucleus. If the valence shell is really close to the nucleus, there's going to be a really strong attraction between the nucleus and that valence shell. If the valence shell is really far away, there's going to be less electrostatic attraction between the nucleus and that valence shell. The third factor is the repulsion between electrons. Now, electrons are all negative, and therefore electrons repel each other. There's another factor that sort of slips into this one, and that's the idea of shielding. Now, shielding essentially, if I come back to this diagram here we're looking at the attraction between the nucleus and the valence shell. The idea of shielding is that if I have a full inner shell, say there, so this might be an atom that's got a full first energy level and the valence electrons are in the second energy level. Because I have a full first energy level there, that inner shell that's full blocks some of the attraction between the nucleus and the valence shell. That idea is called shielding. And shielding reduces the attraction between the nucleus and the valence shell due to that inner shell being full and absorbing some of that positive attraction. So those are the factors that can affect the electrostatic attraction between the nucleus and the valence shell. So essentially we're going to look at the periodic table, and the trends that we're going to look at, we need to identify how they're affected as we go across a period and how they're affected as we go down a group. So I thought, first of all, let's look at how the protons and electrons change as we go across a period and down a group, and then we can use that to explain our trends. So as we go, first of all, across a period in blue, as we go across a period, we get more protons in the nucleus. The electrons are all added into the same energy level, which means there is more electron-to-electron repulsion. So let's have a bit of a look at that. So as we go across a period, say from boron through to fluorine, the atomic number is increasing, 5, 6, 7, 8, 9. That means we're getting more protons in the nucleus. Therefore, we're getting a larger or a greater nuclear charge. As we go across from boron to fluorine, all of the electrons are added into the same energy level. They're all in the second energy level, which means there is no additional shielding. We're not getting more completed energy shells or energy levels between the valence shell and the nucleus. They're all in the same energy level, so there's no additional shielding. And yes, as we go from boron to fluorine, we are getting more electrons in that same energy level, so they do repel each other more. They do try and push each other apart. They do try and expand. They try to get bigger. But as I had written there before, the dominant factor is that there are more protons in the nucleus. So as we go left to right, we are getting more protons in the nucleus. Therefore, we are getting a greater attraction to the valence shell. Okay, so left to right, greater attraction to the valence shell from the nucleus. Now as we go down a group, what we're seeing is that yes, we are getting more protons in the nucleus. Beryllium's got 4, magnesium's got 12, calcium's got 20, so we are getting more protons in the nucleus as well. But we are also getting our valence shell being at a greater distance from the nucleus, and we are getting more layers of shielding between the valence shell and the nucleus. So for example, beryllium's valence shell is in the second energy level, so it's got the first energy level filled between the valence shell and the nucleus, whereas calcium is in the fourth energy level. So it's got the third and the second and the first energy levels all filled, providing 3 layers of shielding between the valence shell and the nucleus. So to summarize, we've got more protons in the nucleus as we go down a group. The valence shell is at a greater distance from the nucleus, and the inner complete shells provide more shielding. And as we go down a group, these two are our dominant factors. That the valence shell is at a greater distance and that there's more layers of shielding. So therefore, as we go down a group, there is actually a decreased attraction between the valence shell and the nucleus. Let's have a look at the trends. The 4 trends that we are going to look at in this video are atomic radii, so the radii of atoms. We're going to look at ionic radii, the radii of ions, the first ionization energy, and electronegativity. We're going to look at how these 4 trends are expressed on the periodic table. So let's first of all have a look at atomic radii. Here's a diagram with some selected elements from the periodic table. You can see that as we go left to right, our atoms are getting smaller. The radius is decreasing. As we go down, you can see that we are getting a larger radius. So let's explain this in terms of our factors. So first of all, the number of protons in the nucleus. Well, as we go left to right, we are getting more protons in the nucleus. Lithium having 3, fluorine having 9. As we go across a period, we are also getting the electrons added into the same energy level. They are all in the second energy level, the 2s and the 2p subshells specifically. So that means that as we go across a period, we are getting an increased electrostatic attraction between the nucleus and the valence shell, because as we go across, we're getting more protons in the nucleus, so a greater nuclear charge, and the electrons are in the same energy level. So there is no additional distance from the nucleus, and there is no additional shielding from the nucleus. So going left to right, we get an increased electrostatic attraction. As we go down a group, you can see our radius gets larger. Now that indicates that there is less electrostatic attraction between the nucleus and that valence shell. Now again, as we said before, the number of protons as we go down does increase in the nucleus. Hydrogen has a lot less protons than cesium. However, as we go down the periodic table, we also get an increased distance from the nucleus. The valence electrons of hydrogen are in the first energy level, and here we have second, third, fourth, fifth, sixth energy level. So we're getting a greater distance from the nucleus. The valence electrons are further away, and we're also getting additional layers of shielding. Cesium has 1, 2, 3, 4, 5 full energy levels between that valence shell and the nucleus. They are all providing shielding, blocking some of that attraction between the nucleus and the valence shell. Therefore, there is a decreased electrostatic attraction for cesium, and it has a larger radius in comparison to any of these elements. So that's atomic radii, how the radius of atoms changes across the periodic table and down the periodic table. Let's look at a couple of examples. Let's look at aluminium and chlorine. Aluminium has 13 protons, chlorine has 17 protons. Aluminium therefore has 13 electrons and chlorine therefore has 17 electrons, and we can compare their 2 electron configurations, and we can see that aluminium has 3 in its valence shell, chlorine has 7 in its valence shell. Both valence shells are the third energy level, the 3p subshell to be specific. So differences between these 2 atoms. Chlorine has more protons in its nucleus, therefore it has a greater nuclear charge. The valence shell is in the third energy level, specifically the p subshell, so there is no additional distance or shielding for any of these 2 elements. Therefore, what is going to be our dominant factor? it is going to be that chlorine has more protons in its nucleus, therefore will have a greater electrostatic attraction to the valence shell, and will have a smaller radius. Let's just check that on our diagram to make sure we've got that correct. Comparing chlorine and aluminium, you can see chlorine does in fact have a smaller radius, and it's further to the right than aluminium. So we got that one correct. Let's look at another element, another example. Here we've got sodium and potassium. Again, I've written out all the data for these two. Sodium has 11 protons, potassium 19. So straight away we can see potassium is going to have a greater nuclear charge. 11 electrons versus 19 electrons. Okay, we need to see their configurations to know a bit more. The old way of writing them, 281 versus 2881, or the new way of writing them, 1s2, 2s2, 2p6, 3s1, so valence electron, and the third energy level, S subshell. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, so valence electron in the fourth energy level, S subshell. So, things we need to think about. Potassium does have more protons, and therefore a greater nuclear charge, but also its valence shell is at a greater distance from the nucleus, and there is an additional layer of shielding. Potassium has the first and the second and the third energy levels all filled, providing shielding. Sodium only has the first and the second energy levels filled, providing shielding. So which is the more dominant factor in this case? Well, as we're looking at a trend where we go vertically on the periodic table, the dominant factor is that we have additional shielding and a greater distance from the nucleus. So potassium will have a larger radius as its valence shell is at a greater distance from the nucleus and has additional shielding from those inner full shells of electrons when compared to sodium. Let's again check that on our diagram to make sure we've got that correct. So comparing sodium and potassium, we can see that potassium is below sodium on the periodic table, and it does in fact have a larger radius for those reasons that we just talked about. Great. Let's take a look at ionic radii. Now there's two types of ions that we need to think about. We need to think about forming cations, and we need to think about forming anions. Cations are ions with a positive charge, and they are formed due to electrons being lost by an atom. Anions are negative ions, and they are formed by electrons being gained by an atom. So what we've got here on this diagram, the atom is represented by the solid line, and the ion is represented by the dotted line. So you can see for all of these ions here that form positive ions, as the atom forms the positive ion, it gets smaller. You can see that's represented fairly well in our diagram. As the atom loses electrons, it becomes the positive ion, which is much smaller. You can see that all the way through. As an atom becomes a negative ion and gains electrons, it becomes bigger. So why is that? Well, let's have a bit of a look at some examples. Let's compare fluorine, the atom, and fluoride, its ion. As fluorine forms fluoride, it must gain an electron. The number of protons that both of these two will have is 9. The number of protons doesn't change when an atom becomes an ion. The number of electrons does change. Fluorine, the atom, will have the same number of protons and electrons, 9. Fluoride, the ion, has gained an electron, so our 9 has become 10. What are the configurations? Well, for fluorine, the atom, the old way would be saying it's 2,7. Fluoride, the old way would be saying it's 2,8. It's got that inert gas configuration. And our new way is to look at it with some more detail. To say fluorine is 1s2, 2s2, 2p5. Fluoride is 1s2, 2s2, 2p6. So what's changed? Well, we've gained an extra electron. It's in the same energy level, same subshell even. So has our number of protons changed? No, still 9, so there's no change in the nuclear charge. Has the distance from the nucleus changed? No, it's in the same energy level, same subshell. Has electron-electron repulsion changed? Yes, it most definitely has. And that is our big factor for forming anions. It's represented quite well in this diagram here. Here's fluorine, our atom. 2, 7. That's its electron configuration. As it gains this electron to become fluoride F-, well, electrons all repel each other because they're all the same charge. So as we add another electron into their energy level, all the electrons try to move slightly apart to maintain that distance they have between them. And so you can see here, when it's become fluoride, its radius has increased, it's got bigger, because the electrons try to spread out to minimize the effects of that additional repulsion by the electron being added in. So that's the electron that's been added in there, and you can see that by increasing the radius, we've maintained approximately the same distance between our electrons. If I just wedged it in there and didn't increase the radius, then the electrons are all closer to each other and there's greater repulsion between them. To minimize the effects of that, the radius increases to keep some separation between our electrons. So that's why an atom becomes larger as it forms an anion, due to that extra electron-electron repulsion. There's no additional shielding, there's no change in nuclear charge, there's no change in the distance of the valence shell. It's all due to that electron-electron repulsion. How about when we form positive ions, cations? Let's compare lithium and lithium plus. Well, lithium has 3 protons in its nucleus. Therefore, lithium, the atom, also has 3 electrons. When lithium reacts and loses an electron, it has 2 electrons, and that's the lithium ion. The electron configurations are 2, 1 for lithium, or just 2 for lithium ion. And we can represent those the new way by saying lithium is 1s2, 2s1, whereas the lithium ion is just 1s2. So what's happened? Has our nuclear charge changed? No. We still have 3 protons, so there's no change in nuclear charge. Has the distance of the valence shell from the nucleus changed? Yes, it has, quite drastically. Here for lithium atom, our valence shell is in the 2nd energy level. Here, the 2nd is gone and it's now in the 1st. Therefore, this valence shell is much closer to the nucleus than this one. So we've gone down a valence shell, or down an energy level from the 2nd to the 1st. So our valence shell is much closer to the nucleus. Is there additional shielding for either of them? Yes. Lithium has a full 1st energy level, shielding the nucleus from the valence shell. Lithium plus does not have any additional shielding. Its valence shell is the full 1st energy level. It hasn't got anything blocking that. So there is additional shielding for lithium, and the lithium positive ion has lost its entire valence shell, the 2nd energy level, to become the 1st energy level, so much less distance. So again, let's look at the diagram. You can see the lithium atom, valence electron in the 2nd energy level, lithium ion, valence electrons are in the 1st energy level. So we've lost that whole 2nd energy level, so therefore the valence shell is much closer to the nucleus, and the shielding of that one, the 1st energy level from the 2nd, is not an issue for lithium plus. Therefore, there is a much stronger electrostatic attraction between the valence shell and the nucleus for the lithium ion than for the lithium atom, and the lithium ion will have a significantly decreased radius. Let's take a look at ionization energy. The definition of ionization energy is the energy required to remove the least tightly held electron from each atom in 1 mole of gaseous atoms. We are just going to consider the first ionization energy, which is the energy required to remove the 1st electron. You can go and look at the 2nd and the 3rd and the 4th, but we're just going to focus on the 1st. So this graph here represents the ionization energy for each element in the first 38 or so. And I'd like to first of all refer to the periodic table before discussing too much on there. So again, remember that we're looking at the trend across a period and down a group, and that as we go across a period, there are more protons in the nucleus, electrons are added to the same energy level, and there is more electron-to-electron repulsion, but no additional shielding. As we go down a group, there are more protons in the nucleus, but the valence shell is at a greater distance from the nucleus, and there are more inner complete shells of electrons, giving more shielding. So those are the two dominant factors as we go down a group. That is the dominant factor as we go across a period. So if we're thinking energy required to remove the outer shell electron, as we have a greater nuclear charge going left to right, there is going to be a greater electrostatic attraction between the nucleus and the valence shell. Therefore, it's going to be harder to pull an electron away from an element down this end as opposed to down this end. That's why as we go left to right, the ionization energy increases due to that increased electrostatic attraction between the nucleus and the valence shell. As we go down a group, we have more and more distance between the valence shell and the nucleus. It's further away, and there are also all those inner layers of full shells giving extra shielding. So as we go down a group, we're getting decreased electrostatic attraction between the valence shell and the nucleus. Therefore, it's going to be easier to remove a valence shell electron. So as we go down a group, the ionization energy decreases. So it increases that way and decreases that way. Sort of the opposite to atomic radii. So let's now have a look at our graph again. So let's have a look across a period first of all. Here's the period from lithium across to neon. You can see as we go across that period, the ionization energy increases. There's a couple of blips. That's due to stability of half-filled and filled subshells. We'll deal with that in another video. So as we go across a period, our ionization energy increases. As we go down a group, like the inert gases helium to neon to argon to krypton, you can see our ionization energy decreases. So that's representing it in graphical form, and we explained that on the periodic table before, the reasons why. Again, across a period, the dominant factor is the nuclear charge increasing, greater electrostatic attraction, harder to remove the electron. As we go down a group, we get more protons in the nucleus, yes, but the valence shell is at a greater distance, with more shielding, decreased electrostatic attraction, therefore easier to remove the valence shell down this end as opposed to this end. Therefore a lower ionization energy. Let's take a look at electronegativity. Electronegativity is a measure of the ability of an atom to attract towards itself the electrons shared in a chemical bond. That could be a covalent bond or an ionic bond. So we're looking at the pulling power, essentially, of an atom towards electrons in a bond. Now let's again refer to our earlier diagram, our periodic table. As we go across a period, what are you expecting to happen for electronegativity? Are these atoms going to pull electrons to themselves more or less than these ones? Well, as we go left to right, our dominant factor is the increased nuclear charge. Fluorine has a greater nuclear charge than lithium. And the electrons are all on the same energy level, so therefore fluorine will have a greater electrostatic attraction between nucleus and valence shell, and therefore it's going to pull on its electrons more, even if it's in a bond. So fluorine has a greater electronegativity than lithium because it can pull electrons in a bond more as it has a greater electrostatic attraction between the nucleus and the valence shell. That's across a period. As we go down a group, what's happening to our electrostatic attraction? It's decreasing because our valence shell down here is at a greater distance from the nucleus than up here, and there are many more layers of shielding down here as opposed to up there. So the electrostatic attraction decreases as we go down a group. Therefore, the attraction between the nucleus and the valence shell has gone down. What's going to be the attraction between the nucleus and the bonding electrons? Decreased. So as we go down a group, electronegativity decreases. That's represented quite nicely on this coloured periodic table here. Now just you can see here that if it's green, it has a very low electronegativity. If it's red, it has a very high electronegativity. So fluorine has a very high electronegativity. Francium has a very low electronegativity. So as we go from bottom left to top right, electronegativity increases. It increases up a group and across a period. So again, why is that? As we go across, increasing nuclear charge, stronger electrostatic attraction between nucleus and valence shell, therefore it is going to have a greater attraction to bonding electrons. As we go down a group, our valence shell is at a greater distance from the nucleus. There are many more layers of shielding, therefore it's going to have less attraction, electrostatic attraction between the nucleus and the valence shell. There will be less attraction to bonding electrons, and so electronegativity will decrease as we go down a group. So those are the 4 periodic trends. I hope you've learned something in this video, and I hope you can explain each of those trends in terms of those key factors.